Welcome back to the Nexperia Power Live event. You're watching our automotive channel. We're about to start with our fourth and already final session of the day.
Here, live with you is Reza for a technical discussion of two automotive applications, including a proposal for the most suitable rectifier technology. The session will take about 25 minutes. We will start with a presentation and then take your questions. Questions are anonymous, and you can ask your question using the question pane on the right-hand side of your screen. Please ask your questions to our expert or share your own experience and insights. And with that, I will hand over to Reza to begin. Reza, please take it away.
Thank you very much, Robbie. Good morning, good evening, according to your time zone. My name is Reza Behtash. I am an application marketing manager at Nexperia, located in Hamburg. And in this presentation today, I would like to briefly discuss the use of diodes in two automotive applications, which are namely solenoid drivers and LED drivers. And I would like to show you how you can achieve extra efficiency and reliability by choosing the most suitable diode in your application. So let's start with a solenoid driver. And let's take a look at the schematic of the solenoid driver. I would like to briefly discuss what is the function of the different diodes in the solenoid driver. So the solenoid is widely used, and from the electrical point of view, it is an inductive load, as you can also see here in this schematic. And at the beginning, if we want to move the valve quickly, we need a high current through the solenoid. Therefore, we have this boost stage at the input, which is boosting the battery voltage to an intermediate voltage. And obviously, this diode here is a boost diode in a switch mode converter. We have a high side and low side switch. The low side switch, called T-selector, is used to select the cylinder you want to address. And the high side switch, T-peak, is controlling the peak current through the solenoid in the starting phase. And once the T-peak switch is switched off, then we need, of course, also a freewheeling path, which is given by this diode. That means this diode at the bottom right is a freewheeling diode. And if I click back and forth, I think you can imagine how it works. And once the solenoid, once the valve has moved, then it is sufficient to have a lower current. This is the hold current, which is provided by the T-hold switch. But also in this case, if the T-hold switch is switched off, we need again a freewheeling path given by this bottom right freewheeling diode. That means this one is an O-ring diode, this one is a freewheeling diode. And at the end of the cycle, if the valve is closed again, we need to deplete the energy in the solenoid. And this is again done by a freewheeling path, in this case, by this diode. So this diode is also, like this one, a freewheeling diode. There's also an interactive application note regarding solenoid drivers. Just go to our website and search for this application note number. Okay, so obviously there are several diodes in this schematic, and due to the limited time of the presentation, I would like to focus on these two diodes. This one, which is a boost diode, will be covered partially by the second part of my presentation, which is about switch mode converters. But for the time being, let's focus on these two diodes. And let's check what are the requirements here for these two diodes. So we see that many automotive customers are using dual die configurated diodes. That means these two diodes are packaged within one housing. We need a low VF since the conduction losses through this bottom right diode is the dominant loss mechanism in this case. We are talking about peak currents in the range of 3 to 10 amps, depending on the application details. So obviously, the lower VF, the better. We need a very low leakage current. This is a crucial requirement from some of our automotive customers. The reason behind is not just some thermal runaway concerns, but also due to the fact that they have a diagnostic current in this system. And this diagnostic current must not be covered or masked by any leakage current, of course. And this is especially the case at high ambient temperatures. In automotive case, it can be up to 130 degrees C ambient temperature. So it's crucial to have devices with a very low leakage current. We need at least 100 volt blocking voltage, taking into account this intermediate voltage given here, 50 to 70 volts. High surge robustness is, of course, key, taking into account an inductive load. And we need a wide safe operating area. As I mentioned, this application is potentially exposed to a high ambient temperature. For example, it could be in the engine bay of a car, for example. So we need products with a wide safe operating area. And last but not least, reliability is, of course, key in automotive application. I didn't mention the switching losses since they are not the dominating part of the overall losses. But of course, also the switching losses are important, especially at higher ambient temperatures. But the switching frequency is quite relatively low. It's typically below 50 to 60 kilohertz. Okay, you see that part of the requirements are technology related, part are also more package related. Technology wise, I would recommend to go with recovery rectifiers. And on this page, you see the recovery rectifier portfolio of Nexperia, 200 and 650 volts. And in particular, I would recommend to use the double die configured products. They come in the CFP15B package, and they are all qualified according to AEC-Q 101 with a maximum junction temperature of 175 degrees C. But the CFP15B package is much more. It can offer much more, and this is what I would like to discuss on the next slide. In the first place, as you can see, it's a clip-bonded package, as shown here in this picture. So we have a solid copper clip. This allows for a low parasitic inductance. It is giving you a high surge robustness, high IFSM. We have this exposed heat sink, allowing for best thermal performance. As I mentioned, we have dual and single die configurations. And very important is the space saving you can achieve on the PCB. So compared to a classical dated DPAC package, you can save up to 60% space on the PCB. I think this is quite remarkable. And last but not least, we have tin plated ends, lead ends. And this allows for an optimized automatic optical inspection from every possible angle. Now let's come to the reliability fulfillments. This is what we call reliability beyond AEC-Q 101. That means we have tested the products in this package according to 2 times AEC-Q 101. We have zero delamination. This is also shown on this picture. So this is an ultrasonic picture after the moisture sensitivity level testing. And would we have some delamination, you would see some discoloration within the package, which is absolutely not the case, showing that we have zero delamination. The most important point is the board level reliability of this package. So CFP15B is fulfilling the board level reliability requirements of one of the major automotive customers. And that means we have done bending tests. As you can see here in this picture, the bending test, by the way, is also a bias test. So the devices are daisy chained and there's a bias and then the board is bended. We have done vibration tests, power temperature cycling, which is a very harsh requirement, by the way, and drop tests. So overall, you can see that the CFP15B package is giving you state-of-the-art board-level reliability, which is crucial for automotive applications like a solenoid driver. Let's go back to the schematic and take a look again at the freewheeling diode. This diode has the highest conduction losses since it has to conduct the peak current, right? That means the parameter to be optimized is VF of the diode. So the question is how we can improve VF without sacrificing advantages which come with a recovery rectifier, with a PN junction, which is the low leakage and the wide safe operating area. So we have been working on that in the recent years, and we came up with a technology based on silicon germanium. And on the next slide, I would like to briefly present you the silicon germanium technology. This is a cross-section of a planar Schottky diode on the left-hand side compared to a silicon germanium diode on the right-hand side. And you see that there is a thin yellow layer of silicon germanium in case of silicon germanium rectifier, which is placed between the Schottky metal on top and the drift layer in the structure. And this thin layer is giving you some very important advantages. First of all, we have an improved IR-VF trade-off. The IR-VF trade-off is also shown here. This is basically the trade-off you have to accept for almost for all Schottky devices. That means if you want to have a low VF, you have to tolerate a higher leakage current. And you see that the silicon germanium diode is positioned in this area. That means it has a lower VF compared to a PN rectifier, but still the same level of leakage current. And it has less leakage compared to a Schottky device, but with comparable forward voltage drop. So it's a hybrid technology in between. The next point is the high potential for miniaturization. Of course, it would be possible to keep VF constant and to shrink the die size and to put the smaller die into smaller packages. We have a Schottky-like switching. So the switching behavior is very similar to a planar Schottky device. And we have a PN-like low leakage current, which results in a very wide safe operating area, which I will show you in a minute, which is stable up to almost 175 degrees C. And of course, all the devices are again 2 times AEC-Q 101 qualified. Now you could also argue why not to use a Schottky device as a freewheeling path in order to reduce the conduction losses. This is a fair question, but then you need to take care and to watch out for thermal runaway issues, which is a critical point for Schottky rectifiers. And in order to highlight this, we have set up a very simple experiment on the next slide. So we have put 2 products with comparable electrical specifications on a thermal chuck. The 2 devices, one silicon germanium, one planar Schottky, are biased in reverse, and we monitor their leakage currents while we heat up the thermal chuck. That means the x-axis is the thermal chuck temperature, y-axis is the leakage current, and you see that at a given point, the Schottky device runs into thermal runaway. The leakage of the silicon germanium continues to increase, but it is still under control. There is no thermal runaway issues with silicon germanium, and this is the huge advantage of the silicon germanium technology. Okay, that's it regarding solenoid drivers. I would like to continue now with an LED driver as an example for a switch mode converter. And this is an asynchronous LED driver. Again, let's take a look at the schematic first. On the left-hand side, you see a LED driver board from NXP. And this board is consisting of a boost converter. The boost converter is necessary in order to compensate any voltage fluctuations which you might have at the input, for example, during the startup of the car. And once we have this intermediate voltage, from there, we use a buck converter to deliver the necessary output voltage. And this very much depends on the voltage across the LED string. So the more LEDs you have, the higher the voltage, of course. So obviously, also in this case, we have two diodes in the boost and in the buck stage. It's the asynchronous boost and buck stage. So the question is, what are the requirements here? First of all, you need a low QRR. QRR is the stored charge within the device, and this charge needs to be dissipated, needs to be removed, and this is causing losses in the MOSFET and also within the diode itself. So we need technologies with a low QRR. The next point is a high thermal stability. LED drivers are also kind of high power density applications. That means we need devices with a wide safe operating area. Again, important for automotive applications. For automotive customers, it is also important to have zero impact of the diode on the EMI spectrum of the converter. So they won't tolerate any increase of the EMI levels. I think this is also very important for not just for automotive, but for all customers. And last but not least, we need also a low forward voltage drop, a low VF. But keep in mind that the switching losses are the dominating losses. But of course, there's also a contribution coming from the conduction losses through the diode. So in order to identify the best technology for such an application, which is a switch mode converter, we started a collaboration with the Helmut Schmidt University, with the department of Professor Hoffman, who is specialized on power electronics. And we realized this double pulse test board. And the special point regarding this test board is the high DIDT, which you can achieve taking into account the relatively low voltage of 48 volts. So we have been able to measure DIDTs up to 1 amp per nanosecond, so very close to the real application. And in order to do so, it was necessary to reduce the stray inductance in the loop. And in spite of this shunt resistor on the board, you see that the stray inductance, the overall inductance is at around 5 nanohenry. And this allows for a high DIDT. And we use this board to measure and characterize different diodes. And on the next slide, I would like to show you a comparison of a planar Schottky to a Trendshotkey. The Trendshotkey is shown in orange, and the planar Schottky is shown in blue. What you see here is the reverse recovery of the two diodes with a DIDT of 1 amp per nanosecond. And as you might know, the area below the horizontal line, below the zero line, this corresponds to the charge in the device. This corresponds to QRR. And this area is obviously much smaller for Trendshotkey compared to the planar Schottky. And you see in this table that, for example, at room temperature, we have 8.6 nanocoulomb versus 26.3 nanocoulomb for the planar Schottky. It's a huge difference. This might be surprising, taking into account that in the data sheet of the Trendshotkey, you will find a very high parasitic capacitance. So don't be confused. The Trendshotkey is the right choice for switch mode converters. And more interestingly, if we go now to a higher ambient temperature at 85 degrees C, there is no increase of QRR for Trendshotkey, while we see a significant increase in case of the planar Schottky. So this is, again, a very big advantage of the Trendshotkey. So at least for the 100 volt class, we don't see any increase at higher ambient temperatures. What does it mean for the LED driver? Now we measure the efficiency of a 48 to 12 volt buck converter, which is a representative tool to characterize such an application. And you see that at 130 kilohertz, we have around 0.6 percentage point higher efficiency with the Trendshotkey compared to the planar Schottky. And if we increase the switching frequency, then of course also the switching losses will increase. And then this gap, this advantage of the trench will become even bigger since the switching losses are more dominating. You might have been wondering about this ringing, which was seen for the Trendshotkey device in the reverse recovery measurements. And you might have been wondering about any impact on the EMI behavior. Therefore, we measured the conducted and the radiated emission of the converter. So you see here on the left-hand side, the Trendshotkey is absolutely on par with the planar Schottky. And also in terms of radiated emission, we don't have any increase for the Trendshotkey device. So that means the big advantage of Trendshotkey in terms of switching is not coming with any penalty, for example, in case, with as a higher EMI spectrum or whatever. And this brings me to the conclusion of my talk. So regarding solenoid driver, I would recommend to use 200 volt hyperfast recovery rectifiers. If you go for dual die configurated products in CFP 15B, you could also benefit from state-of-the-art reliability and also board level reliability. And if you want to optimize your design even further, take a look at the silicon germanium technology. In terms of LED drivers, I highly recommend to use Trendshotkey devices. And this was shown yesterday by my colleagues. There are also some value propositions, unique value proposition for Nexperia Trendshotkys. There you would also have some extra efficiency and some safety margin in the safe operating area. If you want to have more information, please visit our website. You will find also there the interactive application note regarding the solenoid drivers, also information on the Trendshotkey portfolio, and also more details on the silicon germanium technology. Sample boxes are also available and can be ordered from the Power Live page. Thank you very much. I'm very much looking forward to your questions.
Thank you very much, Reza. That was a great presentation. I see the audience is also liking it, but they do have some questions for you. The first one is, when you improve VF of the diode, why does it affect SOA?
Okay, maybe this was not clear in my presentation. Of course, these are two different requirements. You need to improve VF, that's right, but you can't tolerate any impact on the safe operating area. This is the case. In case of Schottky devices, if you have a lower VF, you have to tolerate a higher leakage current, and then you might have also some impact on the safe operating area. This is the point.
Okay. Another question coming in here. Can you please tell us what you mean by 2 times AEC-Q 101 qualification?
Yes, that means that tests has been extended. So, for example, if you have to fulfill 1,000 temperature cycles, we went to 2,000 or even in some cases to 4,000 cycles. And if you have a given requirements according to JEDEC for to AEC-Q 101 regarding the high temperature reverse bias, I don't know from top of my head how long it is the standard, but we doubled that time.
Okay, very clear, thank you. Next question, is the ringing of the Trendshotkey an issue for the application?
Not in the not in the relevant frequency ranges in automotive area. We check that.
Great. Then what is the difference between solenoid and normal inductor?
From the electrical point of view, you can replace the solenoid by an inductive load, this, as a simplified replacement of the solenoid. You can also refer to the previous presentations by my colleagues who explained that in much more detail.
Thank you. Then another question here, Reza. How do silicon germanium rectifiers operate at higher temperatures compared to Schottky and silicon PN rectifiers?
So the tendency will be the same. So also in case of silicon germanium, we have a PN junction in the structure and a metal semiconductor interface. And with increasing temperature, the VF of the silicon germanium will also decrease. And switching-wise, QRR will increase.
All right. Then a question on a topic you mentioned on slide 4. What is the difference between the two freewheel diodes?
Okay, this one has to conduct the peak current. So it has to conduct up to 10 or maybe 20 amps. This one, at the end, has only to deplete the energy in the solenoid. So it can be a much smaller diode compared to this one. So the conduction losses in the smaller one is much lower. This is the dominating guy here. Okay.
Then another very important question here, Reza, to understand from the audience. What is the reason for the improved IR-VF trade-off of silicon germanium diodes?
This is a very good question, which I can't answer in short, but the main reason is the highly doped silicon germanium, which is causing a gradient of the electrons in this thin film. And this gradient, together with a higher intrinsic electron concentration in the silicon germanium, is causing a diffusion current in the structure. So it's a diffusion current coming from the silicon germanium layer.
All right. Thank you, Reza. I have one more question for you. Oh, yeah, one more question for you here. Which kind of diodes should be used in the boost stage of the solenoid driver?
Yes, so here at the input, I would recommend to go with the 100-volt Trendshotkey, and depending on your application, it should be 10 to 20 amps here. And for the freewheeling, which I also didn't discuss, I would recommend to use a 100-volt planar Schottky in the range of maybe 4 to 5 amps.
Good. Good questions. Great answers. So that brings us to the end of this live session. And thank you, Reza, for the great presentation. And if you want to know more about diodes for LED drivers or solenoid drivers, you can follow the research links underneath the screen or chat live to one of our power experts. We also have additional demo content on these diode technologies in our on-demand section. And as Reza already mentioned, we also have a sample kit you can order from this website. And also to conclude for the day, we do have all PowerPoint material and recordings of the live sessions available, and they're available to view on the event platform right after the event.
This concludes our automotive channel on the second day of the Power Live event. We hope to welcome you again tomorrow when we will share with you lots of insightful topics on our GAN channel. For now, thanks for watching and have a great rest of your day.